Hello, we are Team 7. We're presenting our project on deep learning-based visual odometry and loop closure for SLAM. Two important parts of every modern SLAM algorithm are motion estimation and loop closure. Motion estimation is often done by using some form of odometry or by applying a motion model serving as the initial prediction of the robot state. Loop closure, on the other hand, is one of the final steps and allows us to reduce uncertainty of our position estimate and further optimize the map. In this project, we aim to evaluate two deep learning approaches as alternatives to these problems. Beginning with visual odometry, traditional algorithms follow the pipeline shown here, detecting image features in a sequence of images, then matching those features, performing some motion estimation, and finally optimizing. We instead propose an end-to-end deep learning-based approach to improve on the feature extraction by allowing a network to learn which features are important in the input image. The DeepVO model takes in two stacked images, sequential in time, and passes them through a convolutional neural network to extract a 20 by 6 by 1024 feature map. It then uses a long short-term memory recurrent neural network to conduct sequential learning and determine the relative post transformation between the time steps. We trained our model for 100 epochs on 4 different sequences from the Kitty dataset. We calculated the root mean square error using the XYZ positions and got around 27 to 80 meters of translational drift on average across the positions. We overall didn't see a significant improvement in the drift compared to traditional visual odometry algorithms, but the results provide a promising pose estimation for existing SLAM algorithms.
Our first task is to integrate our customized visual odometry into the existing pipeline of ORB-SLAM2. To enable that integration, we need to swap out the post-prediction part within the tracking submodule with our own customized visual odometry. To accomplish that integration, we establish an inter-process communication with C++ client running ORB-SLAM2 and Python server running DeepVO. At each iteration, the client sends the current frame and receives the newest relative pose estimation. Specifically, we use sockets to establish the communication because, first of all, it's synchronous and blocking, which are desired. And second of all, that enables the potential of running deep learning model on different remote machine than the edge device that runs other parts. So the performance was better on trajectories without turns, but it was problematic when the trajectory is more complex. And our second endeavor is to integrate DeepVO with GTSAM, where we use DeepVO as front end and GTSAM as back end. There are two strategies for us to perform the integration. We can either use a batch optimization method or iterative manner. The performance on that was well if post estimation is well enough to begin with, but we encounter problems when the post estimation has larger drifts.
We also have the results from DVL integration with GTSAM. There are more problems. The reason could be the rotation part of pose estimation generated by DVL is not accurate, contaminating the optimization. And the noise used in GTSAM is Gaussian noise, which is hardly encountered in real-world dataset. And the loop closing task is not implemented in this optimizing process. We also have the results from DVL integration with GTSAM. There are more problems. The reason could be the rotation part of pose estimation generated by DVL is not accurate, contaminating the optimization. And the noise used in GTSAM is Gaussian noise, which is hardly encountered in real-world dataset. And the loop closing task is not implemented in this optimizing process.
Apart from visual odometry, we also deployed a deep learning network in loop closing section, especially for face recognition tasks. We wanted to use it as a feature extractor to substitute the original handicrafted feature descriptor. Same as before, we are using socket, but this time we are passing the feature vectors. Here are the results of our work. It actually looks not bad. Due to the various reasons explained before, we have also developed our own loop closing algorithm to equip with our DeepVO front end. It consists of 4 steps, and it involves both the spatial metrics and the visual metrics to make it more powerful. We have tested the algorithm on ground truth poses, and the results look fun qualitatively. So that's the end of our presentation. Thank you very much for your attention and any question.